Alright, so this is part 2 for our look at graphing simple rational functions. I'll put a link for part 1 in the description of the video. So continuing on, we have problem 1 here, 2x over x squared plus 3. So the first thing that we always do is factor. So when we do that, we'll have f of x is equal to 2x over x squared plus 3. It actually will not factor. X squared plus 3 will not factor. One way you can tell is just look at x squared plus 3 on its own. If you just graphed x squared plus 3, that would be a parabola that's moved up 3. It opens up, so it would never cross the x-axis. So that tells you there are no roots for it, meaning it will not factor. So there are no factors for x squared plus 3. There are no real solutions on that would give you x-intercept. So that tells us it will not factor. So 2x over x squared plus 3, nothing to factor there. So now we start looking through our list. Horizontal asymptotes, that's our acronym. I have several videos where we discuss this, but the acronym is BOBO BOTN EATSDC. BOBO stands for if it is bigger on bottom, meaning the biggest exponent is on bottom, your horizontal asymptote is y equals 0. If it's bigger on top, there is no horizontal asymptote, but you likely have a slant. That's only if the degree is 1 larger in the numerator. If exponents are the same, divide the coefficients. That's what the EATSDC stands for. So let's see, what do we have here? Well, it's bigger on bottom, right? We have a first power x term here, second power x power on the bottom. So largest exponent on the bottom means bigger on bottom, so that was this one. BOBO, bigger on bottom, y equals 0 is the horizontal asymptote. So that part's easy. So we have a horizontal asymptote at y equals 0. Vertical asymptotes, looking at our list, vertical asymptotes occur factors in the denominator that do not cancel. Well, we said we don't have any factors in the denominator, so vertical asymptotes, none. I was thinking roots there, none. So that means we have no holes in the graph either, because holes in the graph occur from factors that cancel between the numerator and denominator. There are no factors in the denominator, so we don't have any holes. So x squared plus 3, again, does not factor. That means we have no vertical asymptotes, no holes, because there are no factors in the denominator. All right, now for roots. Roots occur, looking back at our list, roots occur, x-intercepts, from factors in the numerator that do not cancel. So that would mean this factor right here, 2x. We set it equal to 0, 2x equals 0. Solve for x, divide by 2, x is 0. So we have a root at x equals 0. So we're going through the origin. Y-intercept, all right, well, the y-intercept always occurs when x is 0, so we evaluate f of 0. So that would be 2 times 0 over 0 squared plus 3. So that would be 2 times 0, 0 over 3, which is just 0. So the y-intercept is 0. Whoops. Y equals 0 there. Actually, let me put it as an ordered pair. That would be better. So 0, 0 there. For the y-intercept, we pretty much knew that when we had a root at x equals 0. So the domain is x cannot equal anything where we have a vertical asymptote or hole. We don't have any vertical asymptotes or holes in the graph. So all real numbers on the domain. Okay, now we should have everything we need. We'll do sign analysis. In other words, find other points on the graph if needed. But hopefully we have enough here with all of that. So we have a horizontal asymptote, y equals 0. Put some dashed lines in there. We don't have any vertical asymptotes or holes. We have a root, which is also the y-intercept, at 0. So y-intercept again was 0, 0, and that's all we know. So now we know that we have to approach the horizontal asymptote to the far right and far left. So it's either coming in like this or like this on the left side, and either like this or like this on the right side. So based on this information, we have to figure out some other points using sign analysis. So we'll make it as easy as possible. I'll evaluate the function at 1, and I'll evaluate the function at -1, and that should be enough to tell us what's going on. So f of 1 would be equal to 2 times 1 over 1 squared plus 3. I'm just subbing in a 1 for these x's. I chose an easy number like 1 because that makes it easy. So 2 over 1 squared is 1 plus 3 is 4, so 2 over 4 is 1/2. So that would be at 1 comma 1/2, so there's a point right there. All right. We know that we have another point we can evaluate at -1, so that would be 2 times -1 over -1 squared plus 3. So that would be -2 over -1 squared is 1, 1 plus 3 is 4, so -1/2. So we have a point at -1, -1/2, so right here, put that in another color. We have points here and here. So, and we have to cross through here, so we know they connect like this. So I'm going this way. Well, based on what we know with the horizontal asymptote, I have to approach that as x goes to infinity. So I've got to curve down somehow and approach this. Exactly how high that hump goes, we don't know. And then I have to cross through the y-intercept, and right here, and that's also the only root at x equals 0. And I have to go through this point at -1 comma -1/2 down here, and then I must approach this horizontal asymptote as x goes to negative infinity. So it looks something like that. How low this goes or how high this goes, we don't exactly know. We could run some other points and figure it out. Actually, that probably wouldn't be a bad idea, so let's do that. So let's say at x equals 5 and x equals -5, we'll do that. So we'll evaluate. F of 5 is equal to 2 times 5 over 5 squared plus 3. So that would be 10 over 25 plus 3, 28, 10 over 28. So that is something less than 1, so it's actually lower than 1, so it's down here. It doesn't go up very high, that's what we found there. F of -5 would be 2 times -5, so that'd be -10 on top, over -5 all squared plus 3, so that'd be 25 plus 3, 28. So just the opposite, so that would be right in this area. So this hump does not go up very high, and this valley down here does not go very low. So the pink line there has to be the way that graph is shaped.